All right, so let's go ahead and take a look at, ooh, sorry, Eric, too late. You can fast forward through it though. Okay, so what are we doing? Okay, week 2, here we go. So you've made it through week 1 of Math 104, which is one of the probably notoriously one of the most challenging classes in a student's academic career in terms of math. But I think that being said, if you have a pretty good algebra foundation, then it's actually not too bad. So here are a few announcements for week 2. So the ad drop deadline was on Friday, but if you realize that at some point before Friday, November 13th, that this is not working out for you, you do have the option to withdraw. It's something I would definitely talk to Patty about. Patty is a STEM counselor in terms of whether it's better to withdraw or to take whatever grade you think you might get in the course. So there's always things to consider about that. Exam 1, so your first exam will be Thursday, October 22nd, which is this Thursday. It's going to cover chapter 5, 5.1 through 5.4. For those of you who are newer to the class, I would say that lecture materials and quizzes are probably the best resources to help you prepare for the exams. The homework assignments that are on WebAssign definitely don't hurt in terms of practicing the content, but you might find that the flavor of the questions is more similar to the lecture materials and the quizzes, okay? So just a reminder that I'm expecting us to use methods that we learned in class, not some random methods that we found somewhere on the interweb. And for those of you who have not taken an exam yet in this class or with this group of students, so the way it's going to work, you're going to have 2.5 hours, okay, for the exam. You're going to have 2.5 hours for the exam. You'll go through, the first question will be a statement of integrity. I will send that out this week so that you can write it in advance. And then once you have that statement of integrity, if you take that picture and convert it to a PDF, that will be the first question on the exam on Thursday. The second question will ask you to upload a reference sheet. So if you've heard us talking about a reference sheet, then the reference sheet is basically just a summary of the notes. It's usually no more than one side of a single side of paper. You can write down whatever you think might be helpful for you, examples, parts from the notes, whatever it might be, and then that's what you can use to help you during the exam. Let's see, what other things about the exam? So that topic list should be posted already. If you haven't taken a look at the topic list, I would highly recommend that you use that to guide your studying and maybe even guide your creation of your reference sheet, okay? Let's see, question. Were we supposed to still do WebAssign if we did the interview instead? No, if you wanted to do WebAssign, and I think everyone made it really clear what their choices are. So if I have a grade for you in WebAssign, that's the one and I don't have an interview from you, then I'm taking the WebAssign grade. Yeah, I'm gonna post the statement of integrity later, so that'll be something we could all take a look at, okay? Thanks, Richard. Okay. All right, so this week we're going to cover 5.2 today. We're going to cover 5.3 on Wednesday, so that'll bring us to the end of chapter 4. We do have 2 quizzes due this week, so quiz 3 is due on Wednesday and quiz 4 is due on Friday. The exam opens at 9:30 on Thursday and closes at 9:30 on Friday. Yes, Gloria, they are worth the same amount of points. Okay, same amount of points. So for those of you who maybe again haven't taken an exam in this class yet, once you open the exam, you have 2.5 hours. So the clock starts counting. So if you open it at 9:30 on Thursday morning, then you need to submit it by noon on Thursday. If you open it, whatever time you open it, like you finish work at 8 p.m. and you start the exam at 9, that is totally fine. Your 2.5 hours start counting from whenever you open the test. All right, so support things. I feel like most of us are in a groove now, but there is a good study group going, so definitely check that out. I believe it's on a Discord server, which means that it's not going to be flooding your text messages inbox with a ton of different messages, but rather it's a separate app, so you can kind of keep those separate. Val has tutoring sessions this week on Tuesday and on Wednesday, and I had office hours this morning, as well as on Wednesday morning I will also have office hours. Does that work for folks if I do a Monday, Wednesday, and Val does Tuesday, Wednesday? Or the other option is I could do like a Monday, Thursday, and that way, like Monday through Thursday, there's always someone you can ask between me and Val. What do we think? Monday, Wednesday? Monday, Wednesday. Okay. All right, sounds good to me. Okay, so then exam 1 check-ins. So you'll take your exams, I'll get them all by Friday. My hope is to have them graded by Saturday for you. So after exam 1 has been graded, I'm gonna set aside some time to meet with students individually or in small groups. For those of you, if this is your first test in this class, I would love to meet with you just to kind of get to know you a little bit better. Anyway, if you've been with me since August, this is not mandatory unless I feel like maybe we should, develop a good plan to help you find the success that you want to find, okay? So I think that's it in terms of announcements. Were there any other questions that folks had before we got started? Richard, you drinking that tea over there? Like fruit punch or like lemonade? Oh, well, that sounds delicious. All right. So, folks, here's what we're gonna do. Yeah, I had no idea, right? Where do you even get that? Oh, okay, okay. All right, so today we're gonna cover 5.2. And, I spent a lot of time this weekend thinking about what sort of went well last week and maybe what didn't go so well. And so hopefully today's lesson might feel a little bit better, a little bit more streamlined, a little bit more of that same energy that I was having before I decided to give 2 exams in 3 days and grade them all frantically, which never works out quite well, but all right. So, okay. So with 5.2, I know this is out of order compared to the book, but for 5.2, we're talking about the unit circle. And specifically, we're talking about sine and cosine functions, okay? So things that we know, all right? Last week, we talked about the 3 main trig functions. We also talked about the 3 reciprocal trig functions, and we talked about reference angles, okay? And so for the 3 main trig functions, we had sine theta, cosine theta, tangent theta. Then for the 3 reciprocal functions, we had cosecant theta, secant theta, and cotangent theta. Okay. And then we talked a little bit about reference angles. We didn't cover it very much, but we talked about this idea that when we have an angle specifically in standard position, that one of the things we're looking for is where is that initial side And where is that terminal side? Okay. And whatever the shortest distance is angle-wise to the x-axis, that's actually what we call our reference angle. So in this case, this right here is our reference angle. So this angle is its own reference angle. But one thing that we're going to take a look at in a little bit is what happens when we have an angle where maybe the initial side is here and the terminal side is all the way over here. Okay. Now, I think we all know that this angle, if we go in the positive direction, is an angle that is larger than 180 degrees. But when I think about the reference angle is actually from the terminal side to the x-axis, whatever the closest x-axis is. It might be the positive side of the x-axis, it might be the negative side. But either way, that angle from the terminal side to the x-axis is the reference angle, okay? So that reference angle should be between 0 and 90 degrees, okay? So that reference angle should really be an acute angle. And if we thought about changing that notation to radians, how would I change 0 degrees to 0 radians? Or rather, if I change 0 degrees to 0 radians, what would that be? Yeah, we get the 0. And then what about 90 degrees? What's the equivalent of 90 degrees in radians? Yeah, we're gonna get pi over 2, okay? Now I feel like when they introduce degrees in middle school and high school, everyone's like, all right, I got the degrees. And then somewhere along the lines, people introduce radians and people are like, oh, I don't know, these make me uncomfortable. I just hope they go away. Well, they're not going to go away in this course. They're not going to go away in a lot of the next courses. And so really this is, instead of being like, oh shoot, that's the worst news on a Monday, one of the things we should be thinking is like, wow, we have this opportunity in the next 7 weeks to really make sure that we grow in our ability to work with radians just as well as we know how to work in degrees. Okay. All right. So here's a little bit to sort of make us think about what we're going to talk about today. So a few questions that we're going to answer. What is a unit circle? Why do we care about a unit circle? Why is that special? Okay. Where do all the coordinates come from? And then how do we use the unit circle? This is really the point of the whole lesson. How do we use the unit circle to evaluate trig functions and inverse trig functions? Okay. And so that's where we're headed today. And I hope those questions will kind of help keep us centered a little bit. And we're going to start right here with this part. Roman numeral 1, does size matter? Okay, does size matter? So a unit circle is a circle centered at the origin with a radius of 1, okay? So we've got a radius of 1, and if you look up a definition of a unit circle, that's what you get. It's a circle, it's centered at the origin, it has a radius of 1, okay? That in itself is a definition, but what I want us to think about is like, but why? Why did we pick this particular circle? Why couldn't we have picked any other circle, okay? So let's go back to our idea that we talked about on Wednesday for a moment, which is we sort of had like 3 different sized triangles, right? We had like a small triangle, a medium triangle, and a large triangle. And so let's say that this medium triangle, and this was our theta right here, and the side opposite theta was 3, and the side adjacent to theta is 4, and the hypotenuse would be 5. Yeah. So we've got our 3, 4, 5 triangle, right? And if we wanted to write out our sine of theta, I think we would all agree it's going to be 3 over 5. That our cosine theta is 4 over 5, and our tangent theta is 3 over 4. Right? And so that was a review from Wednesday's class, okay? And then we kind of also talked about, like, well, what if you had the same ratio between the sides, but instead of being 3, 4, 5, what if we had a 6, an 8, and a 10? Okay, what if we had a 6, an 8, and a 10? And so if we use the same idea of what we know about ratios, we get sine theta equals 6 over 10, which we would all then reduce to 3 over 5. That's fine. And then cosine theta would be 8 over 10, or that would reduce to 4 over 5. And tangent theta would be 6 over 8, or that would reduce to 3 over 4. Okay. And so that's what we talked about on Wednesday, is that we could sort of have one triangle, and then we could have a different size triangle, but like a larger version of it, and it would still give us the same information, okay? So I hope then our answer to this question, does size matter, as it appears for right triangles and ratios, is that no, the size of the triangle does not matter, because the angle is the part that matters, okay? And so let's visit this pink triangle all the way off to the side for a moment. And let's say that this hypotenuse were 1, okay? So how did I get from a hypotenuse of 5 to a hypotenuse of 1? Ooh, that's really nice. Okay, so Natalia says, I like to think of the angle as a ray, and so no matter how far the ray shoots out, it's the same angle. Exactly. Okay, so if I have this hypotenuse of 1, and I'm telling you that I got it from this purple triangle. So the purple triangle had a hypotenuse of 5. Now I've scaled down the triangle so that the hypotenuse is 1. 5 divided by 5, yeah, okay. So if I think about how do I get from 5 to 1, I did 5 divided by 5, okay. So if we apply that idea, how do I get the corresponding side for the 3? Like, what would the vertical side of the pink triangle be? 3 over 5, right? Because I'm taking that side and I'm dividing it by 5. Okay, what about the horizontal side? How long is that side? Perfect. 4 over 5, because I took the purple 4 and I divided it by 5, right? Every single side gets divided by 5. Okay. So we've divided everything by 5. We've got a smaller triangle now, okay? So now let's think about our sine of theta. Well, sine of theta is the opposite over the hypotenuse. Well, we know that when we take a number, a numerical value, and we divide it by 1, we're going to get that same number. So sine of theta is really 3/5. Well, this 3/5 matches with this 3/5. It matches with this 3/5. So the sine of this angle, which is the same angle for all 3 triangles, is 3/5. Okay, well, what is our cosine of theta going to be for the pink triangle? We follow that same line of thinking. Yeah, we're going to get 4/5 over 1, or we're going to get 4/5. And if we try and figure out our tangent theta, ooh, 3/5 over 4/5. Yeesh. How do we solve those again? Multiply by the reciprocal. Okay, so 3/5 times 5 over 4. Okay, so the 5s reduce, and I get 3 over 4. Well, hey, 3 over 4 is the same thing that I got for tangent theta for the purple one and tangent theta for the blue one. Okay. So why am I making all of us do this all the way down to a triangle, a tiny, tiny triangle with a hypotenuse of 1? Well, if we look at the sine and cosine, okay, we look at the sine and cosine here. The sine ended up really just being the opposite side. And the cosine ended up being the adjacent side. So let me say that one more time. The sine ended up being the opposite side, 3 over 5. I divided it by 1, but I didn't really have to divide by 1 because it gave me the same number. And when I did the same thing for cosine, turns out cosine was just the adjacent side. Well, why is this useful? Well, if I were to tell you that this bottom vertex is the origin, and that this were another point here, what would the coordinate of that top vertex be? Okay, so you went over 4/5 and you went up 3/5. Yeah, okay. Sine of theta is 3/5, and it's an actual coordinate right there. Cosine theta is 4/5, and that is an actual part of the coordinate. Well, that's pretty handy. Let's see if this holds true for the purple triangle and the blue triangle. So let's say again, this is 0, 0. What's the coordinate of that top vertex? The same as what, Thea? Okay. So if we think about how we get to that coordinate, if this is 0, 0, I have to go over 4 and up 3. That means this coordinate is 4, 3. But is 4 the same as the adjacent side? Well, yeah, it's the same as the adjacent side. Like this 4 is the same as that 4, but is it the same as the cosine? And I think the answer there is no, right? So this is not equal, well, let's use symbols. This is not equal to 4. Okay? And if we follow that same reasoning here for the other one, 3 is my y value, 3 is this y value, but the sine is 3/5, which is not 3. Okay. So let's try this one more time for the blue triangle. We've got 0, 0. This coordinate is going to be 8, 6. 6 is this value, but sine is not equal to 6. And same thing, cosine is not equal to 8, even though this is 8 and this is 8. Okay? So all these other triangles, the purple one, the blue one, anything that does not have a hypotenuse of 1 is exactly like Isis says here, which is it's not on the unit circle. This is too big for the unit circle. This purple triangle is really like a circle with a radius of 5. This blue triangle is really like part of a circle with a radius of 10. So it turns out that it is a big deal that we use a unit circle, because not only are the coordinates actually visible on your on the unit circle, but the x coordinate is the same as cosine, and the y coordinate is the same as sine, right? Cosine is 4/5, the x coordinate is 4/5. Sine is 3/5, the y value of sine of the y value of that point is 3/5. So that's why we use the unit circle, because it's not just because, oh, 1 is a nice number to work with, but because we set the hypotenuse to 1, we actually make this so much easier for ourselves, okay? And so if we go back to this definition for a minute, the unit circle is a circle centered at the origin. So this part makes it a little bit easy to sort of deal with mathematically, okay? If you were in Math 116 with me, remember we did like this equations of the circles, and some of them had centers somewhere else, and that just made it a lot harder. But when the center's at the origin, it makes calculations a lot easier. And when we have the radius equals 1, we make our lives even easier calculation-wise, okay? So you might have a different answer for does size matter in other areas of your life. However, for trigonometry, when we're looking at an angle, the size of the triangle does not matter, okay? We'll get the same sine and cosine every time, but what we're gonna focus on is, thank you, we are gonna focus on is the pink triangle, because it makes our lives easier. It gives us sine and it gives us cosine right off the bat, okay? So if you've ever wondered why a unit circle, that's why. Okay, so what we're gonna do now is we're gonna do a quick Desmos activity. Now, I know we've done a few Desmos activities. Some of them I think have gone well, some of them not so well. But we're gonna try this one and see how it goes, okay? So I'm gonna put the link in the chat window for, where'd it go? I'm gonna put the link in the chat window for the Desmos activity. And I'm gonna ask everyone to go ahead and start working on that. So I would like each person to do their own. But I will put you into breakout rooms just so you have a few people to bounce some ideas off of as you're working on it, okay? So let me pause the recording. All right, so cosine of 0 is 1. I like that. Sine of 360 is 0. Anybody get the... No, Desmos is free. So if you go to either desmos.com, you can use the free calculator there, or you could download the app and it's also free. All right, we're not getting to the tangents quite yet, although you are correct. Tangent of 0 is 0, okay? Cosine of 90 is 0, I buy that. All right, we should get sine of 270 as a -1. And then cosine of 180 or cosine of pi should be -1. Good, we got a 0, and then we should have a 1 there, okay? So, I mean, part of this is I want to make sure we know how to use our calculator, right? And the other part of it is I want us to kind of figure out, like, why is our calculator telling us certain things? So if we kind of go back up to the earlier part when we talked about that pink triangle, right? We noticed some things about the sine and the cosine. Like for the pink triangle, which is the unit circle, okay? For the pink triangle, sine of theta was 3/5. And that was also the y coordinate of that corner point. And cosine of theta was 4/5, and that was the same as the x coordinate for that point, okay? So let's see. Let's see if the same thing happens over here. We've got 0, and we've got a 0. Sine of 90 is 1, and check out the y value at 90. Sine of 180 is 0. Check out the y value there. -1, -1, and back to 0, back to 0. Now, that means that when we go back around to all the coordinates again, all those x coordinates should be the same as the cosine ones. 1 and 1. 0 and 0. -1, -1. 0, 0. And back to 1, 1. Okay. So one thing that we might be able to notice here is that the cosines correspond to all of the x coordinates, whereas the sine corresponds to all of the y coordinates, okay? Now, Yitan, I do want to address your point. You said, oh my gosh, they're the same thing, but they're offset, right? We've got this pattern in the yellow. We have 0, 1, 0, -1, 0. And then we have something similar for the cosine where it's like 1, 0, negative 1, 0, 1. And yeah, cosine and sine are offset. How much are they offset by? So close, not quite, not pi. Let's think about sine and cosine are, yeah, by 90 degrees. Sine and cosine are what we call co-functions. Remember we talked about co-functions last week? And so if we were to write what sine and cosine are equal to, we could say sine of theta equals cosine of, that's not a good place to write that. Sine of theta equals cosine of pi over 2 minus theta. That's your shift right there. Okay, so for those of you who were in Math 116, remember we talked about like we should always have the variable first, so negative theta plus pi over 2, and then I drilled this point home in pretty much every test and quiz that we had. What did we need to do here in order to identify the transformations that are happening? Factor out that negative. And if you were someone who was like, why won't she just let that go? This is the moment I've been waiting for like 8 weeks, okay? This is why I didn't let it go. I factor out that negative, I get theta minus pi over 2. So what we have here in the blue is that if I take cosine and I move it to the right, pi over 2, and I reflect it over which axis? Which axis is that negative sign on the inside? Like that negative b value, not a negative a value, but a negative b value. Yeah, over that y-axis. So if I take cosine, I move it to the right pi over 2, and I reflect it over the y-axis, I get sine. Okay, so this right here, okay, this is a little early for this. We're going to talk about this a lot more in the next chapter when we look at graphs of sine and cosine. But I love the connection to what we're thinking about with these numbers. Yeah, one pattern we could see is that sine is all the y values and cosine is all the x values. But another pattern we could see, and it's not different, is that sine and cosine are actually going to be graph transformations of each other. That's all they are. If you shift sine and cosine a little bit, you're going to get the other function. Okay. And if you were not in Math 116 with us and you were like, what are they talking about? You'll figure it out when we get to the next chapter, okay? All right, so what does sine theta represent on the unit circle? What does cosine theta represent on the unit circle? This is where we need to, if you didn't understand anything we did before this, you have to know this next part, okay? So when we think about sine and cosine on the unit circle, all right, we're thinking whoop. Okay, so we've got this, no. Okay, So we've got this triangle. Should kind of look like the triangles we were looking at earlier. Here's our theta. The coordinate of that top point is going to be cosine theta, comma, sine theta. So the yellow one is going to be the sine. The first one, the cosine, is going to be the x value, okay? So if we go back to our slider Desmos thing, right, we should be able to see that now. It should connect to the coordinates that we have. And anybody know how to find tangent from our unit circle? You might know this from before. I think it's an important connection to make. Yeah, it turns out if you want to find tangent on a unit circle, you're going to take the y coordinate and you're going to divide it by the x coordinate. And that's why sometimes you were getting infinity. How do we get infinity out when we divide by something? Like we have a fraction, we want to get infinity out. How does that happen? No, that's the almost answer, not 0 over 1. 0 over 1 is going to give us 0. Okay. But yeah, if I do this, I'll get something undefined. Okay. So I think this is a good time to maybe let's go back to our slide on Desmos. I have too many windows open. Okay. Let's go to that. All right, can you folks see the Desmos? Yeah, okay. So let's start maybe just like at the very beginning here, right? So we've got 1 comma 0. 1 should be our cosine. 0 should be our sine. Now, tangent, they tell us is 0. But if we think about what we just said, tangent is going to be sine divided by cosine, or 0 divided by 1. 0 divided by 1 is 0. That's where they get the 0 from, okay? So now let's kind of like go a little bit more. Okay, so 30 degrees. The x coordinate of that triangle is 0.866. Guess what the cosine is? 0.866. The y value of that coordinate is 0.55. Guess what the sine value is? 0.55. Now, if you have a calculator, go ahead and take 0.55 and divide it by 0.866. All right, so if you take 0.5 and you divide it by 0.866, what are you guys getting? 0.577, or, oh my gosh, check out what the tangent is, 0.577, right? So these numbers didn't just come from like nowhere, but we know that these coordinates exist. And as we kind of keep going around the circle, okay, so x and y value here are the same. I know these are decimals, but sine divided by cosine is going to give you 1 because they're the same number, right? 0.707 divided by 0.707 is 1. So let's see. Is it safe to say that the tangent shows us the slope of that line or ray? I'm not sure I've ever heard anyone describe it like that, but I don't know why I haven't. That's really, really good. Yeah. I think that that tangent is really going to be the rise over the run, sine over cosine. Yeah. Okay. All right. So let's go do this. Ooh, sorry. Too many screens. Too many screens. Okay. All right. Let's do one last piece before a break, which is I want to talk a little bit about complex fractions. Because I think some of us are like, I don't like fractions. And some of us are like, why would you put a fraction inside another fraction? But that's our new reality, okay? So let's do this little piece before we go on break. So working with complex fractions, okay? So when we're working with complex fractions, what we have with a, so if tangent equals y over x for the slope, then it equals the hypotenuse. No, it doesn't equal the hypotenuse because you're thinking about like a squared plus b squared equals c squared. You could find tangent that way, doing a squared plus b squared equals c squared. But if you divide the two sides, that's not going to give you the third side. Yeah. Okay. And yes, for our unit circle, the hypotenuse is always going to be 1, which is nice because when we divide by 1, it means the sine and cosine just fall out to be exactly the coordinate. Okay. All right. So does that mean sine over cosine is the derivative of tangent? You are running before you can walk. But I really like that connection there. I like the connection of the idea to slope. Yeah, yeah. Okay. All right. So working with complex fractions. All right. So I feel like questions like this in the past have probably been like a nightmare for people. Like people are like, oh, I can go grab a calculator. Like, I don't know what that's equal to. Okay. But we're going to see a lot of these complex fractions as we go. And so that's why I want to make sure we know how to handle them. So one thing that we can always do, we can take our numerator and write it. And then we can multiply it by the reciprocal of the denominator. So times 5 over 3. And then we multiply straight across and we get 5 over 6. Yeah. So I think something like that is a fairly straightforward example. And so if I had something like this, okay. So now I have this as a denominator and 1/2 is still my numerator. I can still use the same pattern and I can say 1/2 times the reciprocal of that, which is 2 over root 3, okay? I will say this, I'm a big fan of reducing before I multiply, meaning like I'm not going to multiply straight across because I notice there's a 2 on the top and a 2 on the bottom, so those reduce to 1. And so that's going to give me 1 over root 3. If I didn't want to write this with the radical on the bottom, how would I change it so that there's no more radical on the bottom? Multiply that top and bottom by a radical. Good. So this next part, let's kind of put that in pink. I could do root 3 over root 3. And that will give me root 3 over, what's root 3 times root 3? It's just going to give us 3. Good. Okay. So this is equal to that. Yeah. So if I say 1 over root 3 and then I say root 3 over 3, those are the same thing. Okay. If I want to do this problem, I keep my numerator. I multiply by the reciprocal of the denominator. What's the reciprocal of the denominator in this case? 2/1, good. Okay, and we can do the same thing where we reduce the 2's, and then we are left with √3. Okay. Are these two equal to each other? 1/√3 and √3. Good. These are not equal. Which means are these two equal? And you're also going to say no. Okay, √3 is not equal to √3/3. And I think what happens in people's brains is we just think like, I don't know, I see some square roots of 3's in a fraction, so of course they're going to be the same. Okay, but we want to sort of push ourselves past that comfort point to make sure that we know what's equivalent versus what's not. Okay. One last example, if I do 1/2 and I divide that by 3, how do I use this same structure I've been using to simplify this fraction? I could still write the 1/2, right? That 1/2 is still my numerator. Ah, good. 1/2 times 3, when I flip it, gives me 1/3, so I get 1/6. Okay? So even if the bottom's not a full fraction, you could in your head make it into a fraction so that you can use the same process. Okay? So I just wanted to kind of remind us about that a little bit because we're going to be using that a lot of it when we come back. Okay? So let's see, it is 10:55. Let's go on break until 11:05. It is now. Okay, can't win them all. Can't win them all. My apologies. There are definitely chunks missing for this. Okay, at the angle pi/2, I'm looking for the y/x value. Okay, so let's kind of do that off to the side. The y value at pi/2 is 1. The x value at pi/2 is 0. I know, Mondays. And so this is going to give us the undefined. Okay. And so if you type in tangent of, thanks. If you type in tangent of pi/2 on your calculator or tangent of 90 degrees on your calculator, it's going to give you an error. All right, it's going to give you an error because it's undefined. Okay. And so some folks were saying, oh, it goes to infinity when you were like moving it around the circle. So maybe a more accurate way of saying that is it actually is undefined. Okay. Ugh. Man, I feel so bad about the recording. Okay. So let's take a look at this, and maybe knowing that the first 6 questions were not recorded, are there any other questions on this part before we move on? All right. So we've got one last sort of concept to go over, okay? Um, yes, there are a bazillion things about unit circles. Yes, so quiz 3 should look kind of like this part right here, okay? Like all the different questions, like it'll give you the sentence frame that you fill in, and it'll give you the question as it's asked like in a regular math book, okay? Okay, so one important thing about the unit circle, and there are so many important things, but is that we really want to be able to use it not just to find coordinates, but also to find angle. Okay, so this topic, evaluating inverse trig functions with the unit circle, let's talk about what inverse trig functions are. Okay, so we know that we have sine of theta is our opposite over hypotenuse, right? That's one of our main trig functions. We know that cosine of theta equals adjacent over hypotenuse. And we know that tangent theta equals opposite over adjacent. But what we should also know is that sine is the y value on the unit circle. Cosine is the x value, and tangent is the y over x value, okay? Now, maybe a little bit less well, but we know that the reciprocal of sine is cosecant, and that we just flip the top and bottom of the fraction, hypotenuse over opposite. But what does that mean in terms of a coordinate on the unit circle? Like if I wanted to find cosecant of an angle using the unit circle, what would I look for? Reciprocal y, and how do we write that? One over y, good. So if someone says, find cosecant of pi over 6, you're going to go to pi over 6, you're going to find the y value, and then you're going to write the reciprocal of it. Easy peasy, okay? The reciprocal of cosine is secant theta, which if we flip adjacent over hypotenuse, we get hypotenuse over adjacent. And if we use similar reasoning, it's not going to be the x value, but it's going to be 1 over x value. Okay. And then cotangent theta is adjacent over opposite, and that will just give us x over y. All right. So when we think about the unit circle, now we're moving away from opposite over hypotenuse and moving towards the y value or the x value, okay? But we have a special type of function, okay? It's called the inverse trig function. And the inverse trig function is different from the reciprocal trig function, okay? The inverse trig function looks something like this. Okay. So those of you who were in Math 116 with me, we know that -1 symbol. That -1 symbol we used when we were talking about here's a function, find its inverse. And then I said, I want you to write at the end, not y equals, but f to the -1 equals. Okay, so that getting used to that notation that the -1 means inverse. Okay. So you might have the inverse of opposite over hypotenuse, or you might have the inverse of y. But what that's going to give you is an angle. Like your answer when you do inverse sine is going to be an angle. Now we can follow the same pattern and have inverse cosine of adjacent over hypotenuse, or we might say inverse cosine of the x value would mean your answer should be an angle. And last but not least, inverse tan would be the inverse of opposite over adjacent, or inverse of y over x, which should give us an angle, okay? So if that's probably the most important takeaway from inverse trig functions is that your answer is an angle, right? Whereas all the other ones, your answers were coordinates, okay? So main trig functions and reciprocal trig functions, your answer is a coordinate or a ratio. But inverse trig functions, your answer is the angle. So maybe let's do a few examples to kind of help clarify that. Yeah, for sure. So let's take a look at this. So I'm looking at inverse sine, okay? So inverse sine means I need the angle, sorry. Inverse sine means you're gonna find the coordinate, but you're looking for it in the y value place, right? Because sine is the same as y value. So now I want you to go to your unit circle and I want you to find an angle that has a y value of √3 over 2, okay? So the y value is √3 over 2. Now we find the angle where that happened, okay? So I'm gonna scroll back up to the unit circle and we're gonna take a look. We're looking for where the y value is √3 over 2. Okay. So where is the which angle has a y value of √3 over 2? Oh, we already got one answer in the chat. 60 degrees, cool. And in radians, we also call that pi over 3, okay? If you're like, why won't she accept the degree answer? So I would say for the same reason that at some point my parents refused to answer me when I was speaking in English. They wanted me to speak in Taiwanese so that I would remember the language, so that I would be able to use it and feel comfortable with it. And so part of this too is like, I know we're fairly comfortable with degrees. I want to push us to get to that next level of comfort with radians. Okay, so yes, pi over 3 or 60 degrees is where the y value is √3 over 2. I know, I like writing the pi symbol too. Is that the only place that happens? No, it's not. Okay, yeah, it happens 2 times, right? We have pi over 3 is √3 over 2, and 2 pi over 3 has the same y value, okay? For right now, I would like us to write down both of those, pi over 3 and 2 pi over 3, okay? I do want us to understand when we come back to inverse functions, we're gonna ultimately have to pick one of them. And we'll talk later on about how to pick which one is right. But for right now, we're gonna write down both angles where that happens, okay? So if I go back down to the question, all right, we have the y value is √3 over 2 at the angle pi over 3 or 2 pi over 3. Okay. All right. Well, let's take a look at example 9. I'm looking for the y value and specifically which angles have a y value of -1/2. So go back to your unit circle, find me all of the angles that have a y value of -1/2. 7 pi over 6, or 11 pi over 6. Beautiful. Good. Okay. All right, let's try 11 and 12. I've got the inverse cosine of 1. Okay, so let's think about what that question is asking me for. I want to find an angle that has an x value of 1. What are those angles? Zero pi and 2 pi. Yeah, 0 or 2 pi. All right, what is example 12 asking us for? Like, what could we fill in those sentence frames? The what value is blank at the angle blank? The x value, good, because it's cosine. The x value is -1 at which angle? Okay, and so that's when we go to our unit circle and we look for that -1 in the x coordinate position, and we should get pi. Excellent. All right, so cosine, arc cosine or inverse cosine of -1 is just pi. Okay. Is this kind of making sense? Like how sometimes we find coordinates and sometimes we find angles? Yeah. I know the sentence frames are kind of like a bore, but at the same time, I think that like so much of math is understanding what that question is asking. So if you like the sentence frames, then definitely go with that, okay? Sometimes they only have one angle, and so that'll be like on the pies. Yeah, sometimes that does happen. All right. There are 4 questions here on the the inverse tangent, because I think these ones are a little bit harder, okay? So if I see tangent, I'm not looking for the x, I'm not looking for the y, I am looking for y over x, okay? So as soon as I see that tan, I'm looking for y over x. Now specifically, I want to see which angle has a y over x value of √3. Now I think what makes tangent harder is you're not finding the coordinate. You have to use what we know about fractions and what fraction pair do I divide to get to √3, okay? Now, if I think about the pairs I have like 1, 0, √3 over 2, 1/2, √2 over 2, 1/2, √3 over 2, and 0, 1, right? So these 5 pairs are really the main pairs, and then they get flipped. Like some of them are negative, some of them are positive, okay? But which one of these pairs are worth testing to see if they reduce to √3 when we divide them? Like, should I check 1, 0? Yeah, right? I don't need to check 1, 0. I don't need to check 0, 1. And why don't I need to check this middle one? Yeah, you get 1 when we divide those, right? So you don't have to look at that unit circle and be like, how am I going to test all of the pairs? Be clever. Which ones are worth testing, okay? So this one I get 1/2 over root 3 over 2. And this one I get the opposite, root 3 over 2 over 1/2, okay? This is going to give me 1/2 times 2 over root 3. And the second one is going to give me root 3 over 2 times 2 over 1. Okay? So which one of those pairs is going to reduce to give me root 3? The second one or the fourth? Yeah, that fourth one, right? This is going to give me root 3 when I divide. So now tell me where this angle is. Like which angle has the coordinate 1/2 comma root 3 over 2? And it should be pi over 3, yeah? If you go to pi over 3, you're getting an x value of 1/2 and a y value of root 3 over 2. There's one other place where this happens. Okay. There's one other place on the unit circle where this happens. 5 pi over 3, 4 pi over 3. I say we're going to go with 4 pi over 3. How come 4 pi over 3 works? How come 5 pi over 3 doesn't? Yeah, those negatives. Even though the x and y are both negative, when you divide them, negative divided by negative gives you that positive, okay? So that's why this 4 pi over 3 also. Right? So again, the tangent's definitely trickier, but that's why we have a little bit more practice with those, right? If this is something that you're like, I think I got the sine, I think I got the cosine, then where you should spend your time studying is the tangent part. Study what's hard, don't study what's easy, okay? All right, so example 14, I'm looking for the other one. Okay, and so I think it was John, you who said, like, why is it that they want root 3 over 3? A lot of times the question gets asked that way. And if it gets asked that way, it's important we know how to kind of unpack it to figure out where it came from, okay? So because we have tangent, we're still looking for y over x. And this time we're looking for root 3 over 3, or you can change that to 1 over root 3 if that helps you figure out a little bit better where you're coming from. But that should be the other angle we are looking at, which is the pi over 6. Or what's the corresponding angle in quadrant 3? 7 pi over 6, good. Good, 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 good. Okay. All right, so we've got these last two here. We've got arctan, or inverse tangent is undefined, and then inverse tangent is 0, okay? So if I were to write out both of these in terms of the sentences, I would say for number 15, the y over x value is undefined. Or I might even change the problem to say, I'm looking for a place where I divide by 0. Like that's how I get the undefined. I have to divide by 0. So now I'm looking for coordinates where the x equals 0 or the y equals 0. Yeah, I'm looking for a coordinate where the x is 0, right? So look for where x equals 0. All right, what are our angles where the x is 0? And I think we're going to find pi over 2. And what's the other one? 3 pi over 2, perfect. All right, so pi over 2 or 3 pi over 2 are two possible answers for number 15. Okay. And last but not least, I'm looking for the y over x value where it's 0. So how can I modify like the question so that I'm looking for a fraction where when I divide it, it equals 0? Right? Because I have to compare coordinates. Yeah, exactly. This time I want the 0 on the top, right? Because 0 on the top will give me a 0 when I divide. But 0 on the bottom is when it's going to be problematic. Okay? So which angles have a y value of 0? Zero, pi, and 2 pi. Good. So 0 and pi would be our two possible answers here. Okay. Sometimes we leave the 2 pi off just because it's the same as 0, and so that's why we typically have like the 0 and the pi. Okay. All right. How we doing out there, folks? How are those brains feeling? All right. Flow of class better than last week, worse than last week? How are we feeling? Flow is better. Okay. Okay. Cool. Thank you. All right. So I think we're actually gonna call it a little early today. Okay. So I know this never happens to us. Never ever. Most of the time, I'm like keeping you after.